Welcome. In this session, we'll explore embeddings and kernel functions in the context of support vector machines, or SVMs. Let's consider, as we did in a previous session, let's consider mapping a data vector, to a higher dimension. And this is done in many SVM sources. We'll refer to this as we take a vector that has size n, and the mapping function is phi, and a hook arrow is used to indicate that this is specifically going from a vector space to a vector space. And what we're doing is we're adding at least one and possibly an infinite number of dimensions, and we might also write this as a vector function of a data vector. And one example that we can do is we can say that we're augmenting, and that is we're taking the original data vector and we'll add entries to it. So let's suppose that we have a vector u and that it has n entries. We can embed u into a higher dimension, and for this lecture we'll refer to this as u hat. And the mapping that we proposed in a previous session was if we have a size 2 vector, that what we do is we embed this into a size 3 vector. And we do this by augmenting. And augmentation means that we copy the relevant entries and then we add something else. And we've already been augmenting with, we augmented data vectors and we've augmented weight vectors. Now we're going to augment the data vectors in a different way. And now let's suppose that we take the square of the norm, and that is u1 squared plus u2 squared. And that embedding is a special case of what's referred to as a polynomial embedding. And the reason it's a polynomial is that this is a polynomial in terms of the original entries of the vector. So now suppose that we're given m data vectors, which are of the form xj, and what we do is we now embed those into some higher dimension. So each vector gets embedded independently. And that means that the matrix, the design matrix X that we have, where each row of X is the transpose of a data vector, now that will produce a new design matrix. And this design matrix will have a specific size. That is, the number of rows will be the same as the original design matrix, and then it will be n plus k, where k is the number of extra dimensions that we're adding by doing the embedding. And an ordinary SVM, so the SVM uses x transpose. Let's now consider entry ij of the embedded matrix, embedded design, times its transpose. And each entry, if we look at row 1 and column 1, that would be x hat 1 transpose x hat 1. And then 1, 2 would be x 1 hat x hat 1 transpose x hat 2. And so the entry ij will be x hat I transpose x hat j. And these are the same size of vector, and that transpose can be rewritten as xi hat dot xj hat. And we could further write that as being the embedding of the original data vector times the embedding of the other original data vector. This seems to be more computation than we strictly need. Let's think about this for a moment. What we're doing in this computation is we're expanding the size of this, we're expanding the size of this, and then we're taking a dot product. Well, it seems that for many common embeddings that we might come up with, that there might be a faster way to do that computation. So, for example, let's try this example. So let's try for this, let's try take a vector u and embed it, and then take the dot product of a vector v, and we'll embed that. And that will be u1 times v1, u1 v1, and then it will be u2 v2, u2 v2, and then we'll add to that u1 squared plus u2 squared times v1 squared plus v2 squared. And if we do some straightforward algebra, and I encourage you to take a break now and work out this algebra to confirm to yourself that this is what happens. u1 v1 plus u2 v2, that is u dot v. And then this term you can demonstrate is going to be u dot v quantity squared. And let's observe that in this case we can compute the dot product of the embeddings without computing the actual embeddings. That is, what we did was we looked inside this embedding function, and then we looked inside the dot product, and when we worked it out, we actually didn't need to do those embeddings at all. This leads to a more general result, and that more general result is called a kernel function. And there are an infinite number of these, and fortunately for us, only a finite number have demonstrated to be useful in data analytics with support vector machines. So a kernel function, it has two arguments, and it has two properties. So we can write that as, we'll often write that as the Greek kappa with two arguments. And it must be symmetric to be a kernel function. And that means that when we compute the kernel of u and v, that's the same as computing the kernel of v and u. And the other is that now we'll get quite technical, for finite dimensions, we have if we're using data vectors, then the computations, if we take the kernel function of any two data vectors, then the computations, these produce a positive semi-definite matrix, and we'll call that capital K. And so we can see that this is an example of a kernel function. This will produce a symmetric positive semi-definite matrix for some data. There's a powerful result which is useful if you're in function theory or when you've got an infinite number of dimensions, where the idea of an infinite dimensional matrix doesn't make instant sense. And this is called Mercer's theorem. And the general result is, if we think about how we compute a symmetric positive definite matrix, that means that if we take any vector transpose times the matrix times the vector, that quadratic form has to be non-negative. And the extension is that if we have a square, it's called a square integrable function g that maps a vector to a real number, then the requirement of Mercer's theorem is the extension of this idea of taking a vector transpose times the matrix times the vector. And it's the double integral of, if we take g of any vector v, and we compute our kernel function for data vectors I, j, and then we post multiply by g of v, and we sweep that over all possible i's and all possible j's, that double integral has to be non-negative. And this is the general extension. We won't use the general extension. Well, we'll use the idea of a general extension for one set of kernels. Mostly what we need to do now is realize that there's a way to take a finite set of data and map it to, we can compute the embedding, and when we compute the embedding, we could take the dot product, and we could find that dot product much faster by using a kernel function.